Hi y'all. How you doing? We're here to present. We're the Blue Angels. We're here to present our power tower. And I'm Lewis.
I'm Michael.
I'm Supreet.
Mario.
So basically, our problem statement: we would have to design and create a functional power plant prototype that relies on strictly wind. This is what we wanted to do. We could have went with solar or water, but we figured wind would be better. And we have to meet our acceptable power output requirements, maintain flexibility and adaptability. So basically, we wanted our prototype to be freestanding, functional structure. And basically be cheap. And yeah, the prototype should withstand fluctuating input energy, which can actually span from very high to very low. Go ahead, switch. Yeah. But our design goals is to generate at least 50 milliwatts, achieve functional rotation within the turbine, and have a consistent power output. Which one is that?
So the chief focus throughout the work was a vertical axis wind turbine, and the benefits of it are it's an open system and it's omnidirectional. And the thing is, it's a single system, which means it's so simple and like we can generate maximum output from it. And the thing is, it is compatible for high-low power setting, which means if the wind is blowing too slowly, the blades will still rotate and it will still generate power. So this was our crude design, which we brainstormed during the initial days of our lab sessions. So what we came up to was a stationary axis and a rotating pipe around it. But when it came to build sessions, we couldn't make it into reality. So our actual design is different from this one. This is our actual design which we made up. We have a wooden stick, it acts as a shaft, and we have turbine plates, wooden turbine plates, because they are lighter and it was easier to fix them. And these two wooden sheets, one at the back and half at the front, is to orientate the wind, because if we didn't introduce this blockage, then it would have not been possible for the blades to rotate in a single direction. And we have a gear directly attached under the shaft, so we need not to introduce anything else like pulleys or all that stuff. So we simply attach a driver to the driven gear and attach it directly to a motor, which generates maximum power output. So this was our estimated budget. It came out to be $20.60. Initially, there were materials we bought, but we couldn't utilize them in the best possible way. But towards the end of the build sessions, we bought materials pretty economically and did things pretty good.
So here's the graph of our expected motor curve that we use for our project. As you can see, we have 3 points marked on our graph. We have our no load speed, our stall torque, and then we have the point we expect to run at. So we did an eye test on our project and we let it revolve for a couple minutes. And we measured that it had about 100 RPMs per minute. And our stall torque was around 0.02. So we're kind of expecting a power around 240 milliwatts. So the justification for our design, there's been a couple studies done on vertical wind turbines. In 2030, they're kind of expecting a lot of green energy to blow up. So the vertical wind turbine is a really popular idea because it's omnidirectional. It can withstand very high wind energy, and it's a much more efficient and thoughtful process. So research has seen that it can produce more than 10 times as much power than a horizontal axis, and that's because it is omnidirectional, so it doesn't just rely on wind from one way. It can take wind coming from all sources. And the way the axis is made, the turbines become more endurant and they can withstand larger forces. So here's our justification matrix that we did when we were designing our project. our three ideas where we were trying to compare wind, solar, and air, and then we are going to focus on one source. So we kind of we thought there was a lot of potential for wind and water, not as much for solar because there was only the light bulbs for the competition, and we don't have very much experience with alternating current or circuits. Ultimately, we chose wind, because we didn't want our project to get wet, and the weight of the water could really ruin things. So.
Okay, now, so for issues, we faced a couple of issues. For the first one, the gear test, it was kind of a burden. The way we attached it by nail, and when we attached it, we were hammering it in, and it did mess up the gear, so that's one issue. Another issue was the styrofoam size and attachment. As you've seen in the crew design, we initially planned to use styrofoam for the turbines, but instead the turbines wouldn't stick to the PVC pipe. So just trial and error, we got rid of that. For the turbines, when we replaced them with the wooden turbines, we tested it out, and the fan was blowing air on both sides, so it was kind of counteracting, and there was no spin to it. So, and then for emphasizing the cuts, what I mean by that is we did our cuts of the turbines and the other pieces of wood were kind of imprecise or inaccurate. And the last one, epoxy black application, we didn't use it in moderation. Just next time, just kind of use it in moderation and take it easy on that. And now this is a couple reference reviews. Morello, Lisa, Popular Mechanics, Skill Kathy, wind turbine placement produces 10 horsepower, increased researchers say. That's about it. Thank you for your time.
All right, thanks guys, and I have your guys' permission to upload this on YouTube.
Yes.
No. All right, thanks guys.
No, you too.
So we're kind of expecting to be really close to the stall torque, but we got